Okay,
Very good.
Hmm.
I'm ready. I'm Dustin.
Okay.
Okay. So we are very happy to have Dustin Mixon from the Ohio State University, who will give us another talk on the mathematics of partisan gerrymandering. Go for it.
All right, here we go. Thanks for having me speak. I'm not on the West Coast, but I wish I was. We're going to be talking about partisan gerrymandering. In particular, we're looking at the shape. There's a tension of sorts between shape and something else. Let's talk about shape first. So gerrymandering got its name from making fun of the shape of this voting district in the Boston area. This voting district looks like a salamander, and someone decided to call it a gerrymander to poke fun at Governor Gary, who approved that. And we're still making fun of shapes of voting districts. You can see Washington Post is making fun. And there's actually like a scientific concept of what it means to be a bizarre shape. You can quantify how bizarre a shape is. This is using a notion of geographic compactness, and I'll get into that later. And these notions actually impose constraints on the redistricting process. Several states have a partisan redistricting commission, and the maps that they draw have to meet certain standards, and shape is one of the standards that they have to adhere to. The notion of shape is kind of strange. So on the left is a district that's considered to be a gerrymander, and on the right is a district that's considered to not be a gerrymander, at least to some folks. So on the right, you actually have two Hispanic populations that wanted a common, they want common representation. And so you represent that culture better by connecting them along this road right here. There's this narrow road that connects these two, they're called earmuffs. And that's not considered gerrymandering, whereas this one was ruled as a racial gerrymander. So there's something more than shape that matters in general, and that's one consideration. Another thing people think about is the results of a vote. This is another way for people to indicate how displeased they are with the system. If one party only gets a small fraction of the votes, but they end up with most of the seats, that feels wrong. So one way to measure this is proportionality, where you actually take the proportion of votes and compare it to the proportion of seats. That's called proportionality. Another more recent instance of this is called the efficiency gap, and I'll talk about that later. But there are subtle things here where the state of Massachusetts, for example, is not considered a gerrymandered state, but over 30% of the voting population votes Republican. And you look at the number of US Congress seats that are given to Republicans, you see that there are 0. Out of the 9 there, they're all Democrat, but this is not considered a gerrymander. So there's something subtle happening here as well. We'll actually find that there is a tension of sorts between the shape and the vote, the voting results. This notion of partisan fairness with the electoral result is actually at odds with the geometry of the problem. And that's going to be the focus of this talk in three different parts. And each part is coming from research that I did with these folks. Let's start with part 1, compact gerrymandering. So we're looking at this North Carolina district again. Let's think about why this shape looks weird to us. So you walk along the boundary and you'll note that you jig left and jag right, and that feels pretty bizarre. You might also think about how the shape looks relative to a convex set. Maybe a convex set wouldn't be so bizarre looking. There are ways to use these intuitions to inform an actual number, like a choice of number to measure the extent to which these look bizarre. So one uses the isoparametric inequality that says that the circle is the most efficient use of perimeter to enclose an area. So you can take area divided by the square of the perimeter, and this gives you a number between 0 and 4 pi or something like that. Cool, and that's the Paulsby-Popper score. Another notion passes to convexity. How much does the shape look like its convex whole? So you compare areas to come up with a number. You could also look at the minimum disk, the smallest disk that covers the region, and compare areas there. Another way is to compute moments, like what's the moment of inertia of this thing? You have different notions of nice shapes, and you might wonder, if I force a commission, if I force a map maker, say, to have these nice notions of shape, is he still able to gerrymander? And it turns out the answer is yes, you can still gerrymander even if you're forced to have nice shapes. So you can avoid the Washington Post lambasting your shapes and still manage to help your party out. Here's a cartoon instance of this phenomenon. So the state that we're going to be gerrymandering is a disk, and the voters happen to be distributed along a circle in that disk. And let's say they're half red and half blue, but they're random. So each person flips a coin to decide whether they're red or blue. Okay, that gives us a distribution of sorts. So you might wonder, what is the most geographically compact way to divvy up this state into 2 districts? If I need to break this up into 2 equal districts, what's the least bizarre shape choice? And your instinct is 2 half disks. Cut it up according to a line going across the middle. And that intuition happens to be exactly correct for every notion of geographic compactness in this sense. So this gives us a strong idea of what sort of constraint we should impose. Of all possible splitting into 2 half disks, how hard can I possibly gerrymander? So I do a random draw, and given the random draw, I do the gerrymander as hard as possible. And you can actually analyze this using, like you have this random walk that in the limit looks like Brownian motion, and you do some probability estimates, and you find that half of the time you're able to get 2 districts. And then another portion of time you're able to guarantee 1 district. And then some interesting fraction of the times you get 0 districts despite your best efforts. But the upshot is, even though you only get half of the votes, you're able to score 70-some% of the seats on average. So that's the margin you're able to do. Of course, this is a cartoon model, and there's reasons to poke fun at such models. I don't claim that 70-some% represents the truth, but I am able to run these experiments on real world data. So I took Wisconsin. Wisconsin has 8 US congressional seats. And if you use the vote for the presidential vote between Hillary and Trump back in 2016, you can use that vote to gerrymander with straight lines. So I cut Wisconsin into a straight line. I cut the population in half, and then the 1 half I cut in half again, the other half I cut in half again, et cetera, until I had 8 districts. And you can show that since the Republicans won this state, you can ensure that you'll end up with all of the seats by using this process. It's a consequence of the ham sandwich theorem. But you can also gerrymander for the Democrats using the same process. And it turns out that you could get 7 out of 8 districts go blue in this way. Even you couldn't get all 8 because Hillary didn't win, right? So you had to lose 1 by the pigeonhole principle. But you can force 7 out of 8 in this sense. We don't completely understand what 7 out of 8 is under, like, what's a good model to predict this 7 out of 8 type behavior? How representative of it is it of the real world in general? But what this suggests is restricting the shape is insufficient to combat gerrymandering. You have to restricts something else. And so you might look to impose partisan fairness. And this is the what we'll be talking about in the second part of my talk. So how do you measure partisan fairness? You know lots of ways of measuring bizarre shape. Partisan fairness is measured by proportionality, like you want the proportion of votes to match the proportion of seats. Another more complicated metric that was actually in vogue for in recent times called the efficiency gap metric. This is asking for the number of wasted votes on the left to be approximately equal to the number of wasted votes on the right. Let me tell you what a wasted vote is. If your party wins a district, then any vote beyond 50% is wasted because you didn't need those votes in order to carry that district. If you lost a district, then any votes that were cast in that district were wasted because they weren't used to get a seat. So you count up both types of wasted votes, and you would like the number of wasted votes on the left to equal the number of wasted votes on the right, more or less. That's what the efficiency gap is looking for. For the next result I'm going to show you, we're thinking of a general districting system as a function that receives locations of blue voters, locations of red voters, and a total number of districts K, and then it spits out a partition of your state into K voting districts. And you want certain properties to be satisfied. First, you need one person, one vote. What this says is you want the number of voters in each district to be roughly the same. This is a requirement from, according to the SCOTUS. Another thing, we would like this Halsby-Popper compactness, like some sense in which the districts don't look bizarre, okay? We don't want to end up on the Washington Post for our maps, okay? And then finally, bounded efficiency gap. We want to make sure that we're not wasting too many votes disproportionately, red versus blue. And it turns out that it's impossible to have all these at the same time. And that's kind of sad. That is to say, there exist distributions of voters that make the map maker's job impossible. And the way to do it is you have the voters spread themselves out homogeneously. So in each little square, I have 4 red voters and 5 blue voters. So this is a lean blue kind of state. And in fact, it's lean blue in each of those little squares. So if you were to draw a map that has like straight lines or whatever, then you're not wasting a lot of perimeter. What that means is your perimeter isn't cutting into too many of these little squares. So the interior consists of mostly unbroken squares. So you end up preserving this lean blue phenomenon in each of your districts. So even though 4 out of 9 voters is red, none of the seats turned red. Alternatively, you can try to gerrymander, I guess, in a friendly way, so that you get representation for red and but you end up with these terrible looking districts in order to accomplish that. And you'll end up in the Washington Post, despite your best efforts. There's another instance of this tension between shape and fairness. And we see this in Massachusetts. Like Massachusetts is not considered a gerrymander. The efficiency gap is off the charts. They consider 0.08 to be a good level, and this is at 0.3. It's off the charts for efficiency gap, but it's not generally considered to be a gerrymander. It's not a member of the usual suspects for gerrymandering, because there's more to the story. It's not just the outcome of the vote that matters. Okay. So the third and final thing I wanted to talk about, and this is the thing that I think I was specifically asked to talk about, is the fact that fair redistricting is hard. So the motivation here is when you are asked to draw a map, you have to satisfy a bunch of constraints, not just geographic compactness constraints. You need to make sure that, okay, you need one person, one vote. All the districts have equal population. You need to make sure that counties, not too many counties are split between districts. This is another way to combat against gerrymandering. You need to make sure that municipalities aren't split too frequently. There are other historic things you have to worry about, like the Voter Rights Act and what have you. Lots of constraints that it takes to form a compliant map. And you might wonder, I mean, I know that there's a tension between shape and partisan fairness. How hard is it to find a fair map given all of these sorts of constraints? So hardness, the way to tackle that is with computational complexity. I'm sure this seminar is very familiar with these words, so I won't belabor the point. I want to tell you a little bit about the model we have for compliant versus fair. We're not going to use what the Wisconsin General Assembly uses for compliant. It's going to be very down to earth. We want all districts to have approximately the same population, and we require some notion of geographic compactness. It actually won't matter the details of what our notion of geographic compactness is. Instead, I'll talk you through what we use about those notions in order to get the result. And then you could back out your favorite notion of geographic compactness that gives you those features. And then for fair maps, we just want both parties to receive some level of representation. Okay, so we're going to be thinking about a distribution of voters that are like half blue and half red. And we just want blue to get an epsilon fraction of the seats, even though they have half of the vote. So it seems like a very weak ask here. Can we guarantee, can we find a compliant map that is fair in this very lowball sense? And the answer is, it's actually hard to find out. It's NP-hard to identify a fair redistricting amongst compliant maps. And the reduction follows from planar 3-set. So you'll remember 3-set amounts to, you receive a formula where you OR over different clauses. Each clause is going to have 3 variables in it. And you want to know if there's a Boolean assignment to the variables that satisfies the entire formula. What planar 3-set does is first it draws a graph between vertices and clauses. It's a bipartite graph. And we insist that there exists a planar embedding of that bipartite graph. So this restricts the set of instances that we're interested in. And it turns out that even when you restrict to that subset of instances, you're still going to be NP complete. Okay, so we're looking at certain hard instances of 3-set, namely planar 3-set. And the fact that it's planar, you can imagine it's useful because we're going to be distributing voters on the plane. So once you have an instance of planar 3-set, you're thinking that you'll use this embedding as instructions to place voters in the plane. Okay, let me show you how that's going to go. Okay, so this is a little bit of an eye chart. This is coming from the same instance, like this instance I drew here with x1, x2, x3, x4. I'm somehow blowing that up into a map of sorts where I have a bunch of different towns, and each town is going to have a certain number of voters. It'll be a fraction blue, a fraction red, and we're going to have a notion of geographic compactness that has to be satisfied. And this is going to force our redistricting to take a certain form. Okay, so let me decompress this for you. So I'm actually going to get out of this screen share, and this will allow me to zoom in. Okay, so we're zooming in here. Here's the different types of towns. You have this big clause town, okay? And then you have a small clause town. And then you have all of these blue things are edge towns, okay? And then you have clause adjacent towns in green here, okay? That's how everything's broken out. You should think of clause towns as being like urban areas. So these are very blue, okay? The green you should think of as the suburbs. So these lean red, but slightly, okay? And then these edge towns are more rural areas. This is deep red, okay? Now, our notion of geographic compactness forces a certain feature to happen. So look at all of these edge towns that we're associating with X1, okay? So we have, if we include these clause adjacent towns in green, we actually form a cycle, okay? And our notion of geographic compactness forces us to have a perfect matching between these edge towns. And there's only one of two perfect matchings available, right? Because it's a cycle. So which perfect matching you pick will correspond to whether X1 is sent to 0 or 1. That's this binary thing, okay? Now, if we have two clause adjacent towns that are matched, in this case, thanks to X1, then our notion of geographic compactness makes it so that we allow this small clause town to be districted with this pair of clause adjacent towns. Okay, once these two are paired together, he is allowed to be he's allowed to be sent to that district. In this case, these two clause adjacent towns are matched with edge towns. And if I were to attempt to throw him into their district, it would make that district too wide or something, okay? So that would be not allowed. What this means is that if X1 is good for this clause, like it is in this case, then we're allowed to send the small clause town to this district. And what that means is this thing that used to be lean red is now sent to blue, okay? So now, let me go back to slideshow. So what do we have here? So we're guaranteed to have number of clauses, number of blue seats. Okay, let's say there's K clauses. So we definitely have K blue seats out of this process. We can get up to 2K blue seats if every clause is satisfied. If every clause is satisfied, then we're able to send the small clause town over to one of these lean red districts and make it blue. It's going to be difficult to figure out whether it's possible to draw a compliant map that gives blue 2K seats, because if we do give it 2K seats, then it means that the corresponding instance of planar 3-sat is satisfiable, but that is NP hard to discern. So that's the big idea here. Okay, so this is a worst case result. It doesn't say very much about real world maps, right? I cooked up the map in order to get the result. There is a striking feature where we have this urban thing versus suburb and rural, and you could imagine maybe these feel like roads or something, and you got these rural towns along highways or whatever. But it's still a worst case result. It's not telling you about average case or real world case, but it does give some concept of what is possible to prove about general purpose redistricting protocols. Like, you're not going to be able to guarantee that it works all of the time if your protocol runs in polynomial time, unless P equals NP, which it doesn't. Cool. So overall, there's this tension between shape and fairness. It turns out that it's possible to gerrymander with nice shapes. So if you want to avoid landing in the news, you can still help your party out at the expense of the people. Also, sometimes you need strange shapes in order to get fairness. If you think of fairness as the number of votes resembles the number of seats, sometimes you're going to have to draw a strange shape to get that. that's probably what Massachusetts would have to do in order to get 30% of their seats go to the red. And then sometimes there is a fair map amongst compliant maps, but it's hard to find. Great. So I talked about the main results of the first 3 papers here, and you may have gotten kind of a negative vibe from this talk where democracy is doomed and math says so. And there is some hope that I didn't have time to talk about, where it's possible to design a game that forces partisan map makers to work together and compete in a way that accidentally helps the people, right? You can design a game so that the act of drawing a map, they're trying to work in their own best interests, but their pursuits average out and help the people. So I encourage you to check that out. And at this point, I will entertain your questions.
Thank you very much.